Assalamualaikum. We are from Group 5 C3. Today we will present material balance and equipment sizing for acetic acid production. These are the team members. First is Anis binti Ahmed. Second is me, Nurada Bakis. Third is Nur Yasmini. And last is Muhammad Anas. Content that we will be present today include introduction, process flow diagram, mass balance, sizing calculation, and conclusion. Introduction. The method that we use to produce acetic acid is chemical process. The material that we use is methanol and carbon monoxide. The catalyst that we use is iridium with methyl iodide. The reaction for the acetic acid is methanol react with carbon monoxide. With present of iridium with methyl iodide will be produced acetic acid. The condition for the acetic acid production for temperature is 150 until 200 degrees Celsius, and for the pressure is 30 bar until 60 bar.
So we go to the next slide, which is the process flow diagram. So this is our before process flow diagram, which is we have 4 main components, which is reactor, flash tank, scrubber, and also distillation column. So after this simulation silence, so this is our new process flow diagram, which we have 3 main components for production of acetic acid. So for the first one is reactor, the second one is flash tank, and the last one is the distillation column. If you can see, for the after, we reduce some of the equipments because we want to simplify and for easier for us to calculate the mass balance. So next, I'm going to explain to you the function of each of the equipment. So the first one is the reactor. So the reactor, which we have methanol and carbon monoxide as our raw materials, are fed into the reactor where they are undergo a catalytic reaction to produce acetic acid as the primary product. So the operation condition for the reactor is the pressure must between 228 until 30 bar, and for the temperature it must 180 until 200 degrees Celsius. So for the second equipment is the flash tank, which the reactor outputs flow into the flash tank when unreacting carbon monoxide is separated as a removed as a gas. For this operation condition for this flash tank, so the pressure must be between 2 until 5 bar, and the temperature is about 100 until 150 degrees Celsius. So next, this slide is explained about the role of the distillation column in the production of acetic acid. So the purpose of the distillation column is the distillation column is actually separate and purifies the acetic acid by separating the mixture into 2 phases, which is the first one is the light aqueous phase and the second is heavy organic phase. So the operating condition it have 2, which is the first one is the top of the column, which operates at 1.5 bar and 60 until 90 degrees Celsius, and for the second is the bottom of the column, which is operate at 3 bar and 150 until 230 degrees Celsius.
So we move on to the next slide, which is the mass balance and the calculation involved in this acetic acid production, which is the calculation and the mass balance cover for the reactor, for the flash tank, and also for the distillation column. Okay, next is the production rate. As our group, we do a calculation from the front, not from the backward start of calculation. So this is the information of the production rate, which is our production rate annually is 160,000 metric ton per year, and the molar mass for acetic acid is 60.052 kilogram per kilomole, and 1 ton equal to 100 kilogram, and 1 year is equal to 365 days equal to 8,760 hours. So first we convert the annual production into kilogram, giving us the total of 160 million kilogram per year. By dividing this by the total of hour, which is the hour is 8,760 hour, we get for 18,264.84 kilogram per hour. So we will find this hourly production, and then we want to divide this by the molar mass, so we get 304.15 kilomole per hour. So this is the overall balance drawing for our calculation for mass balance. So after this, we will calculate how to get the answer for each flow rate and each composition. So we move on to the next slide, which is this slide about the mass balance for reactor equipment. So in reactor, we assume the feed inlet is 100 kilomole per hour because we want to make our calculation easier and standardize the equation. And the composition or the composed of 40, which is 0.4 CO, and 60, which is 0.6 CH3OH. And from this, as we know that our team assume the product is 20%, which is the conversion is 80% of CO, it mean by we're gonna get CO 8 kilomole per hour. So we go to make the balance of CO. We will get the composition of Y, which is for the CO 8 kilomole per hour. And then we move on to the next composition, which is CH231 for methanol, and we will get the X of the composition 28 kilomole per hour. And next we go for the composition and mass balance for acetic acid. We will get the composition 32 kilomole per hour. So from this we will get the total B flow rate, which is the outlet stream for reactor, which is 68 kilomole per hour. Next, we go for the mass balance in the flash tank. As we know from the previous calculation, we can get the calculation for the next flash tank more easier because we just use the information, and we must make the overall balance first, which is B equal to C plus D, which is B we already know is 68 equal to C plus D. And then we're gonna make a balance for CO balance. We choose CO balance because it easier of calculation. So which is 0.12 multiplied by 68 will be equal to C. And from this we will know the C is 8.16 kilomole per hour. And then we're gonna get the flow rate from the other from the calculation of the overall balance and CO balance, which is the D flow rate is equal to 59.84. And from this D flow rate, we can know the composition for the CH3OH, which is 0.47, and for the acetic acid CH3COOH, which is 0.53 kilomole per hour. Okay, so for the last slide, for the mass balance in distillation column, as we know, this distillation column, we also make the calculation based on the previous calculation from the flash tank and also the answer from the previous slide. So if we want to get the flow rate, stream flow rate for E and for F, we're going to make the overall balance first, which is 59.84 equal to E plus F, which is we know in equal to out. So next, after we get the first equation, we're gonna make the second equation for the methanol, which is the second equation is 28.125 equal to 0.95 E plus 0.05 F. So from this, we will take the two equation in the calculator, and we're gonna get the answer for E, which is 27.63 kilomole per hour, and F, which is 31.91 kilomole per hour. So from this we will get the total or the overall flow rate for each stream. And for the distillation column, we already know that the bottom is where our product gonna take from.
Okay guys, we continue to the next session, which is sizing equipment for this column. Okay, the first of all is the number of the stages. So as we see in the slide, we can see that the number actual for the stage is 4 multiplied by 4 plus 0.2 equal to 4.02. So for the number theoretical stage, we assume that one of the stage is at the boiling point, so that we get a number actual stage to be minus by 1 to get the number theoretical state. So after we get the number actual stage, we can use this to show for the head of column. So for the head of column, we have two assumptions, which is the first one is tray efficiency and tray spacing. So for the tray efficiency, we assume that the tray is 0.7. So after we divide it with the number of actual stages, we get 5.79. So after that, we calculate the head of column, which is we get 2.87. I assume that the tray spacing for our distillation column is 0.5 meter. For the next slide, is we calculate the mass flow rate for the two component in our distillation column, which is acetic acid and methanol. So our production is focused on acetic acid. So to get the mass flow rate for the both of the component, we need to get the feed flow rate multiplied by composition multiplied by molecular weight. So where for acetic acid is 0.528 kg per second, and for methanol is 0.25 kg per second. So after we get the mass flow rate for acetic acid and methanol, we can continue to the next one, which is volume flow rate. So for the volume flow rate for acetic acid is 0.00502 kg per meter square, and for the methanol is 0.00315 kg per meter square. To get a volume flow rate, we need a density for the two components for acetic acid and methanol. But as our main production is acetic acid, so we get another information with acetic acid at the very first stage. So Okay, we go into the calculation for diameter of this section column. So we assume that for our expression is 0.6 meter. So as we can see in the slide, first we need to show for the maximum vapor velocity U. We can see the formula is right of me. So for the next one is maximum vapor rate. So for maximum vapor rate, we show for our main composition is acid, where the composition have a mole. So 0.0889 kilomole is flow rate, and multiplied by composition 0.95, and multiplied by molecular weight is 1051. So we get 8.846. So after we get for the maximum vapor velocity and maximum vapor rate, so we can calculate for the diameter column. So the diameter column formula have a slide. So after we calculate it, we get the diameter for our distillation column, which is 1.98 meter. Go to the next one is total head column. So for the liquid product, we assume that our distillation need a 5 minutes to get the liquid product. After we calculate the liquid product, we calculate the volume column. So the total of mass flow rate feed multiplied by 300 seconds, which we convert into seconds. So to ease the calculation, we get a 0.25 meter per square. So for the area, we get the diameter from the previous calculation. So after we calculate it, we get a 3.075 square. And after that, we calculate to get the head of product, which is volume per area, so 0.24 meter per square, divided by 3.05 square, so we get a 0.078. So after we calculate the total head column, we get for our final answer, which is 4.448 meter for our distillation column head. We go to the worthiness, so we use the formula the right slide. So after we calculate it, we got 0.96 millimeter. So we go to the next slide, which is assumption. So here I conclude the video and the page where the assumption I doing for our distillation sizing global calculation. Okay, for the last slide for me, which is distillation column, that I will give about our simple drawing and the information about our distillation column. Okay, that's all for me.
In conclusion, this design is based on an assumption to make the calculation and process easier to the student. It is not meant to be used in real life operation.